Madame la conseillère d'État,
Madam Councillor of State, distinguished members of the Grand Conseil, distinguished Mayor of the City of Geneva, former Councillors of State, municipal councillors of the City of Geneva, students, friends, ladies and gentlemen. After the Physics Nobel Prize in 2019, we today welcome the recipient of the 2022 Fields Medal with us today. Geneva University continues its successful career, our head in the stars but our feet firmly on the ground. We're very, very proud of this award given to Hugo Duminil-Copin. We thank him and we congratulate him. And we thank him, as I said, because thanks to him, our university shines as a star on the firmament of world mathematics. And I'm sure that he will continue to allow that star to shine for many years to come. This pays tribute to Hugo's scientific rigor and his creativity. But in addition to this, I know that he also has other competences in terms of personality, a particularly warm personality, and that is also a source of joy to the university. Hugo builds bridges between people and disciplines. Hugo is a born mediator between science and society. He's a talented and passionate communicator. We can't think of any better ambassador with the young people in our country. He will motivate young people to go in for disciplines which sometimes seem a little bit tough and forbidding, but which actually aren't when you listen to Hugo speak about them. Hugo studies phase transition in the field of magnetism, or magnets. From now on, he too is going to be a magnet. He will attract to Geneva other talents from all over the world, just as he himself came to Geneva from France to do his PhD with Dr. Stanislas Smirnov, another Fields medalist who unfortunately can't be with us here today. 4 years ago already, Hugo was quoted as one of the possible winners of the Fields Medal. Everyone has wanted to have him. He was a bit of a messiah at Geneva University, but I think he probably prefers to be compared to Kylian Mbappé. We've talked about this, he and I. Unlike a star footballer, Hugo did not follow the call of other far more prestigious universities than Geneva University. He stayed faithful to Geneva for all sorts of reasons. First of all, because our university and the Faculty of Sciences, and I'd like to greet the Dean of the Faculty of Sciences. Well, as I was saying, our faculty, science faculty, very quickly detected Hugo's talent and appointed him professor literally the day after he defended his PhD thesis. And thanks to support from a well-known Geneva foundation, we were able to offer our mathematicians who are here tonight, we were able to offer them the possibility to leave rather drab premises and allow them to move into a building which was worthy of them. It's a very symbolic medal. It's symbolic in many ways. First of all, it illustrates the excellent links that we have with France. As you probably know, Hugo's career was in France. That's where he got his training. Before he came to Geneva, he's still a professor at the Institut d'Études Scientifiques in Paris. Then he also has very close links with France. But I wanted to thank the Consul General of France, who unfortunately isn't able to be with us tonight for all the efforts he has made. At the press conference in Helsinki, right after the awarding of the Fields Medal, I was able to be there with Madame Sylvie Retailleau, who is the new Minister for Higher Education and Research. She was a president of Paris-Saclay. We know that university very well because it's a member of the League of European Research Universities, of which Geneva is also a member. So I want to say that we would very much like to invite Madame Sylvie Retailleau to the canton, to Geneva. She would be an excellent ambassador. It would help Geneva and Switzerland perhaps to get back into Horizon Europe. The working relations we have with other universities are excellent. Let me recall the very recent opening of the Dubochet Center for Cryoimaging. And also, Jacques Dubochet is a Nobel Prize winner. We have a close relationship with the Federal Institute of Technology in Lausanne, we and Geneva. And this Dubochet Center has allowed us to attract talents which we would not have been able to have otherwise. 4 of the medals which were awarded this year were awarded to people from European countries which are not part of the Horizon Europe program. The third medal was awarded to a professor from Oxford. So the Europe of science must stand united. We must not let ourselves be affected by politics. We'd like to thank the cantonal authorities and the authorities of the City of Geneva for the support they always give the University of Geneva. Today, I think we reap the fruits of investments which were made 10 or 15 years ago. It is our duty to continue to nurture these seeds, not only for the benefit of our university, but for the benefit of the whole of society and the whole of Switzerland. Thank you very much for your attention. Thank you very much. Now I have the pleasure of giving the floor to Madame Barbet-Chapuis, the Mayor of Geneva. You have the floor, Madam. Ladies and gentlemen, allow me, first of all, to extend the same greetings as those just extended by the Dean of the University. As Mayor of Geneva, it's a great honor for me to take part in this ceremony and to be able to congratulate Professor Hugo Duminil-Copin, holder of the Fields Medal winner 2022, and also thank the University of Geneva for organizing this ceremony. As you probably know, this distinction is considered to be equivalent to a Nobel Prize. I'm sure we all feel the same way. I think it's quite impressive to think of all the hard work, the intellectual power, all the efforts which have been put in by Hugo Duminil-Copin to reach this high standard, something which is almost inconceivable for a human being. Yet, Professor, you have been able to make this tremendous contribution to the field of mathematics. And sometimes you really have to think the inconceivable and push the borders beyond what is imaginable to progress in that field. This medal is a reward for your extraordinary scientific achievements, but also to your spirit of curiosity and your attitude, which has enabled you to do this. It's sometimes complicated to understand sciences, but thanks to you, it's going to be possible for us to understand phenomena which it has taken many, many years to describe. You got your doctorate under a former Fields Medal winner, and you yourself said that it's so important to be able to transmit emotions. The best universities in the world now want you to come and work for them, and you're staying here in Geneva. It shows your dedication and your faithfulness to Geneva. I think you like the city, and you also like the mountains around Geneva, which give you an opportunity to climb. Another discipline, which, just like mathematics, means you have to look for the best path, and where you also have to have discipline and endurance. Climbing has actually become an official Olympic sport this year. So perhaps in addition to your Fields Medal in 2024, you could bring back an Olympic medal from the Games in Paris. Well, thanks to you and thanks to the University of Geneva, we are able to enjoy a long scientific tradition, a distinguished scientific tradition for Geneva. So, Professor, may I pay tribute to your brilliant work and your exemplary career. On behalf of the authorities of the City of Geneva, may I express our recognition, our gratitude, and our admiration for the work you're doing in an increasingly complex subject in an increasingly complex field. The City of Geneva expresses its support and also our general commitment to researchers and young talents. We would like to make our contribution to ensuring that they enjoy an environment which is propitious to their research work. I thank you, and I shall now hand over to Madame Nathalie Fontanet, Councillor of State, that is to say, a minister in the cantonal government in the Republican Canton of Geneva. Ladies and gentlemen, I'm also very happy to be able to be with you here tonight, and I'd like to thank the university most warmly for the invitation. It's really a privilege to be able to give a brief introduction on behalf of the Council of State as a tribute to Professor Hugo Duminil-Copin for this extraordinary distinction. I have already had an opportunity to chat with him. We're not going to discuss mathematics. He promised that, and I promised too. So there won't be any mathematics. That's going to help me, I think, get through my speech. He is now an official ambassador for Geneva's academic excellence. But I'm not sure whether it's a good idea today, and I'm looking at the dean now. I'm not sure whether it's a good idea to continue to call him professeur ordinaire, which is the French term for professor, full professor, because I must say, Professor, there is absolutely nothing ordinary about you. In the eyes of the public, you've become something like the Roger Federer of science. I had no idea that you had other sporting preferences. I could have used that, but let's face it, Roger Federer is from Switzerland. He's Swiss. And Switzerland and the people of Geneva feel very strongly about Roger Federer and admire him greatly. That's why I made that comparison. So the University of Geneva has got into the habit of producing champions. This Fields Medal is the fourth Fields Medal that has honored the University of Geneva. This meeting here this evening, thus, once again, gives us an opportunity to point out the high standard and quality of our academic institutions and the way in which they distinguish themselves in such a cutting-edge discipline. It's a huge source of pride to the cantonal authorities, the fact that our university has such tremendous talent and is capable of attracting such wonderful talent, and also to be able to reap the fruits of so many years of hard work. I think Hugo Duminil-Copin's work helps us to understand the behavior of matter and are probably going to be able to be applied in some economic field. And it also probably holds out promise for new industrial developments and economic applications. Ladies and gentlemen, there's a long tradition for mathematics in the canton of Geneva. In October and November, we project some beautiful artistic images on this very building on the university. This coincides with the Right Symposium, a scientific symposium. When you see how young the professor winning the Fields Medal is, I think that gives us hope and should encourage our young students and those who are even younger or not yet students, give them hope that they can follow in his steps. So with this Son et Lumière, which we have, as I said, in October and November, is in a long tradition of academic achievement. Madame Wiazowska, Marina Wiazowska, is also a winner of the Fields Medal. So the Lake Geneva area is not only famous for finance and other matters, but it also shows the high standard of scientific research there. And it also demonstrates that not only men can be good at mathematics, because we have a woman winning the Fields Medal this year. Science, ladies and gentlemen, is the product of teamwork. When you see how complex the world around us is, it's obvious that it can only be understood by constant cooperation. Not to be part of the Horizon Europe program is unfortunately going to cut us off from innovation. Therefore, it is of crucial importance that there be interaction between researchers all over the world. It's absolutely crucial that we continue to train the best talents or attract the best talents. Otherwise, Geneva is going to lose its ability to grow brain power. We don't want to lose our best powers because we are not able to motivate young talent. It's quite clear that the state, the public authorities have a key role to play here, and Geneva's Council of States will continue to pursue this endeavor, and the university as well. And all this together, all of us, each one of us, has to contribute to making this materialize. We must continue to keep these universities attractive to young people. That's one of the keys to success. And the free movement of ideas is an absolutely essential part of all this. I now have the great pleasure of handing over to Madame Elsa Floret. Thank you to the Dean, and thank you, Madam Councillor of State, and the Mayor of Geneva. Thank you all. If I say spider and Fields Medal, I'm sure you know who I'm referring to. And you know that only very recently a spider crawled into Hugo Duminil-Copin's biography, just at the time when he won his Fields Medal. And this Fields Medal was probably the tool used to squash the predatory arthropod, which had just scared Anaëlle, Hugo's 15-month-old daughter, in the middle of my telephone interview with Hugo on Monday. He won the battle with the Araneid, and I was able to continue my interview with Hugo. Hugo was always a comfortable student. He was comfortable at school, and he trusted in his capabilities. And like many young men, he wanted to be a fireman, an astronomer, and then a teacher, the greatest profession in the world, just like his teachers. And he wouldn't be here today if he hadn't had a bit of a shock, if he hadn't got a slap across the face, as he himself puts it. And that is when he was anti-penultimate in his first maths test when he started at high school in Paris at the Lycée Louis-le-Grand. Until then, in all his previous schools, he had always been top of the class. And as you can imagine, very soon he was back there first in the class. And he was able to fully develop his ambitions. And he was able to become confident in his favorite discipline, which is mathematics. So how did he and Geneva meet? It took him a while to fall in love with the city. He arrived in the autumn when the town was covered by low cloud and fog. It was a shock to him coming from Paris. There was no one in the streets. He didn't know that all the people of Geneva were up in the mountains, up above the fog. It took him 6 months to decide not to leave Geneva. And since then, he has discovered that there is no fog up on the top of the Salève. Or maybe he's decided to go to the Valais, to a chalet. I don't know. So how does he work? In 2018, he was already in the running for the Fields Medal. But in spite of that he was on the cards, he hasn't changed his working method. And even though this idea was somewhere at the back of his mind, it hasn't changed his way of working or the way he does his research or how he transmits ideas. He has never focused his work on winning prizes, although he's won any number of them. He has always remained true to himself. He's never tried to optimize himself or in any way move away from his regular way of functioning, of working. He has stayed true to his ideals, and whereas some mathematicians are determined to present things in as difficult and complicated a manner as possible, he goes for the simplest formula. He wants to show that it's easy to solve a problem. It means he presents things in a natural manner. Of course, that takes time, and you have to think about proof, and you have to transform it, and that takes time by definition. But he still has this inner flame. He's not afraid of the Nobel Prize syndrome. He's not going to rest on his laurels. He's not about to lose his passion for research. Hugo Duminil-Copin says that what he does is physics mathematics rather than probability, because physics mathematics brings together the two passions of his youth, maths on the one hand and physics. Maths because of the rigor of that discipline, and physics because of the intuition and the curiosity that goes into understanding natural phenomena. He sees the boundary between these two disciplines as a continuum, and in Geneva, he was offered his professorship during the cocktail party that followed the defense of his thesis. Hugo is also a permanent professor at the Institut des Hautes Études Scientifiques, which institute can boast 8 fields medals and is located in the town where he grew up, Bure-sur-Yvette. As a high school student, he had no idea that this very prestigious school was situated right there in his town. Does chance come into it when you're a probabilist? Hugo, over to you now.
Thank you very much for those kind words of introduction. You know that I like mountain climbing. There are a few smiles at the back of the room. These are colleagues of mine. We climb the Selève together. But don't rely on me too much for the Olympic Games. I think that I won't be ready in time. So I won't spend too much time on the first part. Afterwards, you can ask questions. But before that, I was asked to say what I do in life, to give you some indications. And I have to do it in front of 400 or 500 people. So there will be no formulas. This is a promise that I make. So it'll be rather pleasant for you. You'll have a lot of pictures, a few videos, a few clips. And quite interesting clips in terms of the mathematical aspect. So, why do I do what I do? How I do it? How do I carry out my activities as a mathematicien? I won't go into the how too much. So, what is on the screen? Well, From Coffee to Mathematics, so that's the title. You'll soon understand why. So, what do I do in life? In terms of research, and everybody realizes that a university professor does other things than research, he teaches. And this is not the idea, of course, of this evening, is to give a lecture. It would take me 2 hours, and I'm not sure that that's something that you would relish. So I will talk about science, work as a researcher, and the area in which I've specialized is phase transition. So the first question is, what is a phase transition? So you might not understand all of the words that I use, at least the first time that I use them, but then I will try and provide explanations so that you can better understand them. So what are phase transitions? You know them. These are changes in the state of matter. And of course, the best known one is water, which you have on screen. The phase transition, the change of the state of water. If you take water molecules, you lower the temperature to 0 degrees. What happens? It becomes ice. What has happened? We had a system and we changed the temperature. That's not very complicated. We lower the temperature gradually. You can do it as slowly as you want or quickly if you want. But at 0 degrees, it changes to ice. The water molecules are going to reorganize themselves in a certain configuration, ice. And if I heat the water to 100 degrees, we get vapor or steam, so we know that transition. All of those of us who actually cook pasta. So this applies to other physical systems. It is a sudden change of the behavior of a system. We vary parameters very slightly and very gradually. There are many lights on the ceiling, so I cannot look above. I'm just looking at the people in front of me. But I do have you in mind.
Super. J'aime bien. Je vais redonner des trucs ici plus souvent, je pense.
I'm going to give lectures here more often, I believe. I quite like this room. So that is the first example that I wanted to give you. There are other examples, and here you're going to see something very rare, a mathematician who carries out an experiment. So this is a very special moment. Please enjoy it. What am I doing? I'm taking a magnet, and I'm going to heat that magnet. I had to use 10 matches before I could actually heat the magnet. So this is what I'm doing. What happens? So you heat the magnet, trying not to burn yourself. These are rather special magnets. Magnets that you can actually buy in a shop, but they do have peculiarities. And when you heat this type of magnet, what happens? Well, the magnet, the magnetization or magnetism became so low and the gravity became strong, and for this reason the magnet fell off the screw. So this is what happens when you heat a magnet. And when a magnet has iron, the temperature that you have to reach is 760 degrees. So this is a different type of magnet with less iron. But whatever the magnet, there is a temperature at which it ceases to be a magnet. So this is a phase transition. You vary the temperature gradually, and you go from a stage of magnetism to a ferromagnetic state to a paramagnetic state. That is the phase transition that I really enjoy. And I will come back to it a little later. So these are two examples. I think you've understood what a phase transition is. A third example is on the screen, percolation. What is the idea here? The idea is to study material porosity. If you grind the coffee beans, you put the ground coffee, and this is a an espresso. What else? I was told not to mention brands, but it's a bit difficult. So during your questions, you can use brands as well. And I was told that I actually looked like George Clooney, and I was a bit vexed, I must say. Because it was ironical. I believe there was some irony. But nonetheless, George Clooney and coffee. So if you put water here, the coffee grains are not going to let water through, and it will be impossible to make coffee.
Si au contraire on tasse pas
If,
assez,
on the contrary,
l'eau passe extrêmement facilement.
you don't
Va pas du
press
tout récolter
down
les
the
arômes
coffee,
du café,
well, the
et on
water
aura,
will move more slowly
américain.
through the
Il n'y a pas
coffee.
d'Américains dans la salle, c'est bon.
But the risk then is to have American coffee or filter
Allemand, même si vous êtes
coffee.
américain, vous êtes dans la salle, vous n'êtes
So
pas
you have to
attaché au
reach
café
the
américain,
right
donc
balance
ça va aller.
between
Et puis c'est pas retransmis sur Internet de toute façon, hein, ça n'arrive jamais. Donc,
pressing them or not pressing the coffee that you
donc
are
le but
preparing. So
de la personne qui fait du café, c'est d'essayer
aim,
d'exactement
of course, is to reach the right balance, to be at the stage of transition,
c'est dur pour l'eau de passer.
and to make it difficult for the water to flow through the coffee. And there is a halfway point that
où l'eau ne passe plus,
actually
donc de
separates
la zone
the
imperméable
situation
à
where
la
the
zone
water
perméable.
doesn't
C'est
flow
cet
through,
endroit-là
and
qui va
it
être
does
en fait
flow
le
through
moment où
the coffee,
l'eau
and it is
passe,
at that
mais
moment
dans des
that the
méandres
water
qui sont
actually
suffisamment
flows through the
complexes
coffee, but
pour qu'on récolte
in a
bien
complex
les arômes du
route,
café,
and
qu'on
in
fasse
this
un
way
beau
you get a
café
very
italien.
rich coffee with full aromas,
Donc là, de
true
nouveau, il y a une
Italian
transition
coffee.
de phase.
So
Si
there,
vous
there's
dites
phase
que, bon, faire
transition.
du café, c'est peut-être pas la motivation principale qu'on
And
puisse
if
imaginer.
you're not
Pensez
highly
à-
motivated
en
in
fait, c'est
drinking
quelque chose qu'on peut
coffee,
voir
well,
dans
you can see this
dans
in
tout
other
processus
examples.
de porosité, en
In
particulier,
any
on peut imaginer le
porosity
charbon.
process, such as
Et c'est
coal,
voir
for
quel type
instance,
de gaz passe à travers le
what
charbon.
type of
Ça,
gas
c'était même le
actually
principe des
passes
masques à gaz
through
pour
coal,
se
and this
protéger,
was the
des
principle
choses
of gas
comme ça.
masks
C'est quoi le
to
principe? C'est que ça
protect
va laisser
oneself
passer
during the World
les gaz
War
avec
I.
des molécules qui sont
The
relativement petites, en
idea
particulier
is that
l'oxygène.
gases such as
En général,
oxygen with
intéresse
small
la personne
molecules
qui
can actually go through
Et ça,
coal.
pour peu, ça filtre
But,
les gaz avec des grosses molécules.
Gases
Et,
with large
du coup, ça
molecules are
évite de
filtered,
se retrouver avec,
and in this way
des gaz toxiques.
you can avoid toxic gases such
dans les
as
poumons.
mustard gas
là, de
in
nouveau,
your
En
lungs.
fonction de la taille des
So,
molécules,
depending
par
on the
exemple, en fait,
size of the
aussi en fonction de la
molecules,
température du charbon, parce que plus on chauffe le charbon,
more
plus il
you
va
heat
devenir en fait,
the coal,
imperméable au
more
gaz,
it
plus
becomes
petits seront
impermeable
les
to
molécules de gaz qui
gas,
peuvent passer.
and the
C'est de
smaller the
nouveau une
molecules that
transition
will be
de
able
phase
to
ici
filter
où on
through
essaye de
the
savoir justement
coal.
de se
Well, there
placer
again,
de telle
there's a
sorte qu'on laisse
phase
passer, par exemple,
transition,
l'oxygène
and there we want
pas des,
oxygen to be able to flow through the coal, but not larger
J'en
molecules
profite
that
pour
are more
donner une
dangerous.
référence,
So
là-dessus,
one
parce que
reference
c'est
here,
un étudiant en thèse à moi, Mendes
one of my students,
Moulamara, qui l'a remarqué.
Mendes
Et
Moulamara,
je
who
trouve cette
noticed
référence
this,
très
and this
très
reference is
intéressante.
very interesting.
Pendant la guerre, Rosalind Franklin
Rosalind Franklin,
a
during the
fait en
war,
fait exactement des expériences
carried
sur
out
le charbon,
experiences on
pour
coal
justement savoir à quel
to
point
be
il
able
était
to find
perméable au
out to
gaz
what
en fonction
extent
de la
it was
température.
permeable to
Et
gas
Rosalind
depending on the
Franklin,
temperature.
donc, c'est quelque chose qu'on ne connaissait
And
pas du tout, mais
Rosalind
en fait,
Franklin,
d'un
this was
certain
not
point de
something
vue,
that
c'est
was
la
well
première
known,
expérience, en
and
tout
this
cas,
is
c'est
the
la
first
plus vieille que je
experience, or
connaisse,
the oldest
qui
experience
soit
that I'm aware
reliée
of,
à la notion de
that is
percolation.
linked to the concept of percolation that I will
Mais
discuss in a few
Rosalind
moments.
Franklin, c'est aussi
Rosalind
une chercheuse
Franklin
qui a eu un impact
was a
très
researcher
important dans la
who had
découverte
a
de
significant
la forme
impact
hélicoïdale
on
de l'ADN.
the discovery of the
D'ailleurs, a été un peu
helicoidal
spoliée,
form
de
of
sa
DNA.
découverte. Donc je voulais la
And
mentionner puisque,
I wanted to
bah, c'est
mention
quand même
her
assez
name
impressionnant,
because what she did is
d'avoir
very
des contributions comme
impressive.
ça dans différents domaines,
And she was able to contribute
des
in
sciences,
various
et
sectors
d'arriver
of
à ce que, à
science,
chaque fois,
which is very
malheureusement,
impressive.
peu de gens s'en souviennent, donc
And
c'est
very
important
few people
derrière
remember
de
her,
remettre
so
en
it's
valeur.
very good to
Donc,
recall
Rosalind
her
Franklin était
name
une très
in
grande
an occasion
scientifique
such
et
as
je
this
voulais
one. She was a
le
major
mettre
scientist,
en valeur ici.
and I wanted to recall
Juste
this
une petite
this
référence,
evening.
un mathématicien est une machine pour transformer le
A
café en
mathematician is a
théorème, Paul
machine for turning coffee into
malheureusement,
theorems.
c'est une
Paul
citation qui est tout le
Erdos,
temps utilisée.
this is a quote that is
Ce qui est
very
très
often
énervant, c'est qu'elle est
used.
très vraie. Donc,
And
du coup, voilà,
the
je
problem
voulais
is
quand même vous la
it's
mentionner.
very
Et
true.
on va maintenant passer
So I wanted to
à la
mention
question
it.
que vous
So
posez
we come to the
toutes
second
et
part of
tous,
my
à mon avis,
presentation.
c'est, mais où sont les
Where are the
mathématiciens?
mathematics in
Moi, je
that?
suis
I'm
venu
sure
voir un
you're all
mathématicien
asking
et
that
on parle
question.
de phénomènes
I've come to see a
physiques,
mathematician,
du
and
sport.
he's talking to us about
Qu'est-ce qui se passe?
physics,
Où sont les maths?
chemistry,
Alors.
sport.
Où est-ce? Commençons par la porosité.
So let us start with material
Donc, le
porosity
but
in the
du
mathematical
mathématicien,
sense. The
quand
aim
on fait de la
of
physique
the
mathématique comme
mathematician,
moi,
when
c'est
you
d'essayer d'expliquer
do
le
mathematical
plus simplement
physics
possible
as I
pourquoi
do, is
une
to explain in a
phase
simple
doit
way
avoir lieu.
why a
Pourquoi?
phase transition
D'un
is going to
certain
take
point de
place
vue,
or
c'est un
not.
miracle de la
Because
nature
it's a
qu'à
miracle
une
of
certaine
nature to a
température,
certain extent that
il y ait
at
un
a certain
changement
temperature
complet de
there is a
comportement
complete
quand je prends les mêmes
change in the
molécules
behavior
d'eau,
of
où je
molecules
prends
of
le même
water, for
charbon,
instance,
où je prends
the same
le même
water,
aimant.
the same
Qu'est-ce qui
coal,
fait
the
que
same
les choses
magnet.
changent? On a
How
envie de
can I
comprendre ça.
explain that things
Donc, ce qu'on
change
va
at a
faire, c'est
given
qu'on va faire une
temperature?
caricature
So we're
mathématique
going to do a mathematical
qui
caricature, this will enable us to explain what is actually happening before our very eyes, caricaturally, of course, but this is what we're trying to do. And on the basis of this small mathematical model, we're going to try and understand whether there's a phase transition or not. In the case of percolation, this is quite simple. The idea is to modelize the matter or the material as a labyrinth. I'm trying to find out whether water can go through my coffee, whether gas can go through my coal. So what am I trying to do? I'm trying to look at the water and the coffee as a sort of labyrinth where water or gas can move, can meander, and it can follow a certain itinerary within the labyrinth. And given the fact that these are very complex systems, if you take coal, there are many molecules in coal. If you take coffee grains, there are many coffee grains in the coffee pot. So you're not going to try and take an accurate picture of what's happening, but what you can say is that you don't know exactly what the inside of my coffee pot looks like. So I'm going to take a random graph, and I'm going to see whether randomly I'm able to explain what is happening in the phase transition.
Donc on fait ça avec le nom savant, ça s'appelle... ah oui, alors, je peux essayer de pointer autant que je veux, là ça va pas marcher. Le nom savant, c'est graphe aléatoire.
I call this a random graph, that is the scientific name.
Je peux sauter, donc vous venez de voir le problème des ponts de Königsberg, et hop, vous le voyez plus.
And you have the problem of the Königsberg bridges, so I don't have to explain that, fortunately. But how do we proceed randomly, and how do we produce this graph? You have a tiling with angles and corners and borders, and I'm going to decide which of the edges are red and which ones are white. In red, the liquid can flow through, in white, not. So I take Field's medal, for instance, and for each edge, I'm going to try not to lose the medal that I've just won. I can decide, depending on which side I flip the coin, that the edge can be white or red. And I do this for each of the edges. It is not complicated. If you have time, I think that you would be able to draw up a graph. Now, imagine that you have a coin that is biased, that doesn't always, that there is a gretter chance of flipping on one side than the other. And in this case, you would have more red than white. And depending on the value of this trend, to have heads rather than tails, whether this will change anything to the reasoning. And this is why you will understand why mathematicians are interested in mathematics. It's when you see this type of picture, what is happening here. There are two pictures of percolation. What I've done, I haven't colored in red and white. What I've done is that once I had drawn my random labyrinth, I colored the various areas where I can go. So in blue, you can go to all those areas. The person... Green. The colors are not very clear on the screen, unfortunately. I'm not a painter, as you have concluded. So red, you can go to all those areas. Remember the edges that let the water through and the others that don't. And here you have P, which is worth a 0.49. So there's slightly more tails than heads. And there's 0.51, slightly more tails than heads, so a little more red here than there. Red being not maybe the appropriate color, but what you can see here is that there's one area where you can go from everywhere to everywhere using the red edges. Whereas here, even though you have
on peut pas du tout.
quasi
Vous
the
voyez
same
que chaque
number of
personne
red
est bloquée
edges. You
dans
can't. Each
une région
person
de l'espace
is
qui est très
blocked
limitée.
in a
Comment on
certain
interprète
area
ça?
of the
Ici, on
available
interprète
space.
ça comme la
So how
partie
can you
où
interpret this? This is the part
le
where
matériau est poreux.
the material is
L'eau
porous,
passe facilement. Si je
water
mettais de l'eau en
passes
haut, elle arriverait
very
en bas sans
freely and
aucun
very
souci.
easily
Ici,
from top to bottom,
je suis dans un matériau
whereas
qui est totalement
here
imperméable.
the material
Pour un
is
mathématicien,
totally
je veux bien croire que c'est
impermeable.
juste pour un
So for a
mathématicien, mais pour un
mathematician, this
ici,
is something
on a
that
une
is a very
description à la fois de ce qui est
interesting.
poreux
Here
et de
you
ce
have
qui
a
ne l'est pas.
description of what is porous and what is
D'accord? Donc
not
c'est un modèle
porous.
mathématique
It is a mathematical
pour la
model
porosité. De nouveau, je
relating
pense
to
que
porosity.
je vais essayer. Wow, c'était moi ça?
Was that
J'ai des
me?
super pouvoirs, hein. C'est génial.
I have superpowers.
Ouais, je devrais
How
dire
wonderful.
que j'avais prévu des vidéos, mais apparemment il y a du son. Et elles ont été faites en.
I had
en
thought of
humeur
showing you a
pour
few
la
clips,
Et alors il y a une musique, mais.
but the music is very
C'est pas
loud.
moi qui les ai faites, mais.
So I didn't produce those video
apparemment, ça
clips.
pulse, quoi. Après, si vous voulez rester, on peut.
If you stay on
on
after
danse
the end of the
là-dessus.
presentation, we
Alors,
might even be able to dance on this
Maintenant,
music.
qu'est-ce qu'un aimant mathématique? On a vu ce qu'était la
Now,
porosité mathématique.
What
Je vais
is
vous
a
donner
mathematical
juste une idée de
magnet?
ce qu'est un aimant mathématique, et
We
après,
talked
je vous
about
montrerai deux,
mathematical
trois images
porosity,
là-dessus, ne vous inquiétez pas.
and
J'ai
I'm
aucune
just
idée
going to show
comment
you a
le
few
projet.
pictures.
Donc, la description de l'aimant mathématique, elle était plutôt pas mal dans la vidéo. Donc, qu'est-ce qu'on va faire? On va imaginer que l'aimant, en fait, il est fait de plein de petits. Ouais, vous
So
pouvez enlever le
again,
son. Il y a
we
pas,
use
il y
probability
aura
to
pas de
construct a system, and this is called the
son. Ouais. Donc, qu'est-ce qui s'est passé ici?
So
On a
what
pris un
happened
aimant,
here? We took a magnet
et on a imaginé qu'il était fait de
and we
plein de
imagined that
petits,
it
ce
was
qu'on appelle
made
des
up
dipoles, des
of
petits constituants qui sont
dipoles,
faits comme
little
des petits aimants.
components, small magnets in fact.
Et ensuite, on a
And
imaginé que ces
then
petits aimants,
we
plutôt
imagined
qu'être
that
complètement
these
n'importe
little
où,
magnets,
je vais
instead
faire
of
ce
being
petit-là,
randomly
on a
distributed
commencé en se disant qu'il y
throughout
avait
the
une multitude de petits
magnet,
aimants dans mon aimant.
these small components.
Et après, on a fait
dipoles.
deux hypothèses. On a fait une première
And
hypothèse
then
qui consistait
two
à dire
hypotheses
que
were
les petits
made.
dipôles,
First,
en fait,
that
ils
the
sont placés
dipoles are
régulièrement.
positioned on the intersections of
On
a
appelle le
regular
long d'un
grid.
réseau. C'est quelque chose qui mathématiquement aide
or a
énormément
lattice.
le scientifique.
And this is something
La deuxième
that
chose
is
qu'on
very
fait comme
helpful for
hypothèse,
mathematicians.
c'est que
The
les
second
aimants
assumption
peuvent pointer que
is
dans
that
deux
the
directions, nord ou
dipoles
sud.
are like small magnets pointing in
Pas,
one
on
of
a des
two
petits aimants.
directions,
on
either
veut qu'ils
north
pointent
or
soit au nord,
south.
Et bien ça permet exactement
And
comme pour la percolation,
that, just
exactement
like
comme
for
vous tirez au hasard
percolation,
un labyrinthe,
or for drawing
un
a
graphe aléatoire.
random
Ici,
graph or a labyrinth,
puisque le phénomène est très
here,
compliqué,
given the fact
on va
that this is
juste
a very
simplifier
complicated
en disant
phenomenon,
qu'on a ces petits
we're going
dipoles
to
qui sont placés
simplify the
régulièrement et qui
reasoning.
pointent
We
soit vers
have
le nord, soit vers le
dipoles
sud.
that point
Et on
either
va,
north or
juste
south,
dire que,
and we're simply going to say
on va juste tirer au hasard, excusez-moi. Je devrais m'excuser, j'ai pas eu le temps de le préparer parce que
my
je suis
apologies,
occupé
I
de tout le monde est malade à
didn't
la
prepare
maison
this in
et
detail.
c'est
I had to
déjà
look
un
after my
miracle
daughter.
absolu
Everybody
qu'il y ait
is
des
sick
slides.
at home,
Je veux dire,
so it's
je
quite a
suis depuis
miracle
2
that
heures du
I
matin
even
et,
have slides
aujourd'hui,
with me.
Anaël a dit non, tu ne révises pas.
And Elle said, no.
Donc voilà, je suis désolé.
No looking at your
Mais
presentation
donc de
again,
nouveau,
so
on tire en fait au hasard
I wasn't
l'aimant.
able to
Et,
rehearse the
de
presentation.
nouveau,
My
en fait, on peut
apologies.
étudier exactement comment on
So,
peut
but
faire
coming
des
back to the
simulations
presentation, so the
de,
dipoles are like small magnets pointing either north or south,
de la
and
percolation.
they're positioned
Ici,
on
on
the
peut faire une
intersections of a
simulation
regular
de
grid.
ce que serait un aimant.
We can do a
Donc ça,
simulation
c'est un
of what
aimant
a magnet
mathématique.
would be. This is a
Et en fait, les
mathematical
couleurs, c'est
magnet,
quoi? Les
and the
petits points
colors
blancs,
are what?
c'est
The
les
white
petits
dots
dipôles qui
are the
pointent,
little
on va dire, vers le
dipoles
sud.
that are pointing
Et les petits points
southwards,
noirs, c'est les petits
and
dipôles
the
qui
black
pointent vers le sud.
dipoles are pointing
Voilà.
northwards.
Les mathématiques, elles sont là, dans le sens
So
c'est quoi? On fait
the
une
mathematics
caricature
are there.
mathématique
This is
du
a
phénomène
mathematical
physique.
caricature of
Et
the physical
après,
phenomenon.
advienne que pourra,
And
il faut bien
then
que quelqu'un arrive à trouver quelque chose dessus.
We
Donc,
will
qu'est-ce qu'on trouve
see
dessus, par exemple? Je vais juste ça,
what
vous
we
allez
can
voir,
deduce from this.
c'est plutôt simple à comprendre. Fameuse
So
transform.
phase
En général, quand
transitions
quelqu'un vous dit
come
ça, c'est qu'il y a
in
strictement rien à
two
comprendre
distinct
qu'ici.
families.
Mais
This
là, je
is
vais essayer
actually
de
quite
dérouler
easy
la
to
règle.
understand.
Donc, les transitions de phase, elles viennent en fait en deux familles.
So
Il y a
there
deux
are
types
two
de
families.
transitions.
There is a discontinuous family
Il y a
and
des
the continuous
transitions de phase qui
family.
sont
There are
discontinues.
phase
C'est ce qu'on vient
transitions
de voir ici. Si vous prenez
that
de
we
l'eau,
have seen. If you
vous
take
la
water,
mettez
for
par exemple
instance,
au congélateur,
you put it in
vous
the
savez très bien
freezer,
qu'à
you
0
know that
degré,
at
quand
0
vous ressortez
degrees
la bouteille
Celsius,
et qu'il y a de la glace, elle a soit explosé,
the
soit
volume
chanceux,
will
mais
increase and the
au
bottle
mieux,
might
elle aura
explode
changé de
in
volume.
your freezer. So the volume has changed.
En fait, à 0 degré,
At
le
0
volume
degrees.
change discontinuellement. Si j'essaie de
And
dessiner le volume,
this
je ne
happens
peux pas garder le
discontinuously.
crayon
The change in volume is
contre
discontinuous.
contre le papier, je suis obligé de sauter à la
you have
nouvelle valeur
to
à 0 degré.
jump
C'est pas
to a
ce qui
new
se passe du
value
tout
at 0
quand
degrees.
je
This is
regarde
not
le
what
magnétisme.
happens when I look
Quand je
at
regarde le
magnetism.
Et que j'évalue par exemple, donc avant je regardais le volume pour l'eau.
A little
Ici,
earlier I was looking at the
j'évalue
volume for
la
water.
force
Here I'm
magnétique.
looking at the temperature.
Et ben quand je la dessine, ce que je
And the,
trouve, c'est
magnet
qu'elle
not sticking
descend
to the fridge, you may
quand
remember
j'augmente la
that.
température, c'est assez rassurant, mais elle descend continuellement pour atteindre 0 exactement.
And
à un
there
point,
is a continuous
justement
drop
l'endroit
to
où on
0
perd la propriété d'être un
in the
élément.
magnet,
Au-dessus, on
and
n'est
where
plus un
the
élément,
magnetic
au-dessous, on est un
property
élément.
is lost.
Là, la
Lost.
transition
Above
phase,
that,
elle est
it is a
continue parce
magnet.
que je peux dessiner
Below, it's no
cette
longer
courbe
a magnet. So
sans
the
lever mes
phase
traits.
transition is
J'essaie d'éviter
continuous.
d'utiliser le terme de fonction continue, puisque je sais qu'il y a des gens qui
I don't want to
derrière
use
ne
the
dormiront pas très bien.
term continuous
Se remémorant
function,
leur cours de
because
collège.
this might
Donc
bring
j'éviterai ça,
sad
mais
memories
voilà,
to
il y a
some
deux types de
students
transitions de phase.
who followed
Eh ben,
such courses
je vais
at
vous dire
high
juste un
school.
résultat.
So there
Vous
are
voulez
two
juste atteindre ça.
phase
Un résultat
transitions that are possible.
que-
In terms of
pour
the
lesquels j'ai
results
reçu la
that are
médaille Fields.
interesting, and this is one of the
Comme ça vous
reasons
donne
why I
une
was
idée.
awarded
Parfois,
the
c'est pas
Fields
si
Medal.
compliqué non plus d'aller jusqu'à juste un
It's
résultat.
not so
de
complicated after
mathématicien.
all.
Et ce résultat, il dit quoi? Il dit
And
pour
what
la,
does the
pour la
result
caricature
says
de magnétisme,
that
pour
for
ça s'appelle le modèle
caricaturing
d'Ising, le modèle qui était cette caricature du phénomène de
magnetism,
magnétisme
the
des aimants.
Ising 3D model,
Pour cette chose-là, eh ben, en fait, la transition
well,
de
the
phase,
phase
elle est bien
transition
continue.
of the
Alors,
3D
vous allez dire,
Ising
mais,
model is continuous. That is the result.
voit.
You might think
On peut juste, là,
that
je
this
vois les
is something that is obvious. And there are
J'avais vu un aimant, mon
physicists
cher.
here in the back of the room saying, well, have you never seen a magnet? Have you never held a magnet in your hands? Have you never heated a magnet? Well, yes, I have. But I reached the conclusion that the phase transition of the 3D Ising model is continuous.
On a envie de comprendre de façon
And
générique pourquoi ça a lieu pour tous les
we
aimants,
would
quels que
like
soient les aimants
to
qu'on pourrait
understand
imaginer,
why
par
this
exemple,
happens
etc.
for any
Donc, la
type of
caricature
magnet. So
mathématique,
generically,
elle a ce
and the
pouvoir
mathematical
de
caricature
décrire
has this
ce qui se
power
passe de
to be
façon
able to
générique.
describe
Et
in a
du coup,
generic
bah,
manner what is
avec tout
happening.
pouvoir vient quelques responsabilités, quelques difficultés même, je dirais, plutôt dans ce cas-là. C'est que c'est très difficile d'arriver à
I must say
démontrer
that it
ce type
is
de
very
propriété.
difficult
Et
to
c'était le
demonstrate
sujet de ce
this type of
La bonne
property. It
nouvelle
was
là-dessus et
the
la
subject of
motivation,
this
c'est
theorem.
que, en fait,
The
les
good
transitions
news
phase
is
continues,
that
c'est, elles
continuous
sont toutes
phase
douces,
transitions
toutes
are very
gentilles par rapport
soft,
aux
very
discontinues, elles se passent,
gentle.
c'est plus féminin, il y a plein de
more
choses qui se passent
feminine.
derrière. En fait,
There are
derrière,
lots of
dès
things
qu'on connaît, on sait que la
that
transition
happen.
phase est continue,
We
il y a
know
plein de
when a
choses qui
phase
se passent au
transition is
point critique,
continuous, so there are
en
all
particulier à
sorts of
l'endroit où la
things that
transition
happen
phase se
at
passe.
the critical
Il y a ce qu'on appelle des
threshold.
symétries cachées,
There are hidden
fluctuations, etc.
symmetries,
Et
strong
c'est quelque chose qui est
fluctuations
très,
of strong
très
symmetries rather,
intéressant à étudier
and this is something
physiquement et
that
qui
is
a
very
donné avec
interesting to
beaucoup
study
d'autres.
physically and that is connected with many other topics of interest.
Je vous donne juste une citation, on va
A
lire ensemble.
quote maybe from Kadanoff,
C'est une citation d'un très très grand scientifique qui s'appelle
a
Kadanoff.
major scientist.
Il dit, la
He
stratégie
said the
consiste à
strategy
étudier
of
une
studying
question
a physical
physique en
question
utilisant des
using
modèles
largely
largement
simplified models.
Je suis d'accord que en fait ces
And
caricatures
I
mathématiques
agree
sont
that
des
these
simplifications.
mathematical caricatures are simplifications,
Et justifiées
is
par une
justified by a
caractéristique des
characteristic
systèmes
of
physiques
physical
appelée
systems
universalité,
called universality,
stipulant que les
which states
propriétés
that qualitative
sont les mêmes en
properties
fait quand on parle de
and
différents
sometimes
systèmes.
even
Il y a quelque chose, c'est comme
are the same in
c'est
different
un
systems.
cadeau de la nature.
This is a gift of nature, so to speak. I explained one way to caricature a magnet. If you find a similar way of caricaturing a magnet, well, the both systems are going to behave in the same ways. This is robust. It is resilient from the scientific viewpoint. This is very good news. What I describe as a mathematician is very close to reality. It really doesn't depend on the simplification of what a mathematician is trying to do, and you may end up with a result that is completely different. So this is very robust. It's this concept of universality. As the moment you have universality, it is interesting to find the justification of the simplest possible model to study these phenomena. So, a caricature. And I think you recognize me, a very simple model of me. I will just finish with a few pictures. Oh yes, so we can skip that. What is the life of a mathematician, the daily life? So we struggle alone on a blackboard or a whiteboard in this case. And sometimes several of us are straggling. We were so cute when we were young, and I absolutely wanted to include these pictures in my presentation. This can last for hours, trying to understand the problem with the equation on the left. Sometimes we obtain a result, we start writing on the screen. These are mathematician tables, just to give you an idea, mathematician blackboards. If there is amongst mathematicians in this room somebody who understands what's on the blackboard, well, I'd be very impressed. But just to show you what this looks like visually, months of research, in fact. This is the end result. And then there's a final product which looks like this. This is mathematics, not as many formulas as you might expect. And I was a little kind with you because I decided to include one or two formulas, but not too many of them. And then the monsters gallery to finish off, various models, and they're just to give you an idea of what can motivate a mathematician. When I look at that, I think this is a fascinating pictures, and I really want to understand what is happening. Why does it look like this? Why does it resemble that? Why does it behave in such a manner? Thank you very much for your attention.
Merci beaucoup.
Thank you very much. There are many of you here at Bastion University, and there are also many following us online with simultaneous interpretation. And I'm sure there are many Americans wondering what to do with their percolator and whether American coffee is back here. We thought very soon you'll have a video of this conference on the university's website. Initially, we thought that we'd have this question and answer session in nature so that we could allow our brains to do what they're best at doing, namely think and ask questions. But I can just see that all sorts of clever questions are going to come out of the audience. Let me begin with one. 15 months now after having been awarded the distinction of a happy and hands-on father, you were awarded the Fields Medal. Which of these two events were you the worst or best prepared for, and which takes up most of your time? Well, if I look at today, my daughter wins hands down. Of course, we're always prepared. Of course, what I was looking forward to most of all was my daughter, obviously, and I perhaps wasn't as well prepared as I would have liked to have been. You learn quickly. Well, one learns. You learn because you don't have any choice. And now, members of the audience, there are 3 roving microphones available if you have any questions. Is there a first question? Please take the plunge. I can't see what's going on at the top on the balcony. Yes, the lady in the second row, you have the floor. Thank you very much, Hugo. I have a question. I've heard several of your interviews and read several interviews, and you've showed lots of pictures. You tend to speak about mental images. The transition from a picture or an image to an equation is something that interests me. It's a discontinuous transition. Well, it worries me too, actually, because there are several stages in the creative process, and it depends on the mathematician. I have a very visual way of working. I think less in equations than in images. The first stage consists of finding the right image, and unfortunately, sometimes transforming this clear mental image or this clear drawing into a formula or a sequence of formulas which really work, well, that's the beauty of mathematics. Sometimes it works, sometimes it doesn't. Sometimes it works a lot better than you think, and sometimes the image turns out to be far more expressive than the formula, and far more expressive. There's always this uncertainty. Just at this particular point when you go from the image to the formula, that's the discontinuous point, or the point of discontinuity, should I say. There's a gentleman in the third row over on the right.
À droite, pardon.
Over on my right.
Les passages.
Merci.
Merci beaucoup. Bonsoir, félicitations. Je suis député.
Thank you. I'm a member of the local parliament, but I'm also a coffee roaster. I have a question. I'm also a member of this beautiful university in Geneva. I have a question for you. It's to do with excellence. You embody excellence, thanks to your Fields Medal, the excellence of the university. But I wanted to ask you about failure. You said, or actually, when you were being introduced, we were told that you were stimulated by the fact that you did so badly in a maths exam. And in the local press, you also said how damaging bad grades and notes can be. And you say that there is this tension, permanent tension. How do you reconcile all this? I think I can easily reconcile the two. My education, my upbringing, the way my parents brought me up is such a way that I was exposed to many things. There were so many things I didn't know how to do. I was confronted with so many things I didn't master that I was used to making mistakes. I was used to failure. It's not something that bothered me more so much that it mattered. So I was really prepared when that maths failure hit me. I was prepared to react in a positive way and be motivated. I'm not sure that everybody would do that today, because I don't know if that's the way we bring up our children. I believe it's particularly true of mathematics. This systematic tendency to say that failure or mistakes are the best thing that can happen in mathematics, and that mistakes must be banned. I think it's a very bad thing, because it's not in line with our natural tendency. How did you find time to continue with your research work? Everyone wants you. Your diary is full for the next year, maybe even more than a year ahead. How do you manage to do your research? Well, I'm an optimist. I don't look at what my diary holds in store beyond the next week. Well, then I have my holidays. But I think I know that there's a day. I know that there's one day where I guarantee one day that I can do my research work. Someone looks after your diary for you. Yeah, but don't tell anybody that. There are other things, in addition to research work. I have other things in my diary, but don't mention it, because the person who looks after my diary is here right now. So we won't talk about it. Okay, next person in the third row. Thank you very much. Could you talk a bit about the different dimensions? How high does it go? Up to which dimension? You showed pictures in 2 dimensions and 3 dimensions. Is it conceivable that you might go to an even higher dimension? Well, that's the beauty of these maths models. They originate in order to make it possible to describe a physical phenomenon. For the magnets, for example, we want the Ising model illustrated in 3 dimensions, because magnets are 3-dimensional, or dimensional, even though what I showed you was in 2 dimensions. But they can be generalized in all dimensions. As mathematicians, we're totally free. We're not limited by a laboratory or we can give free rein to our imagination. The easing model could be seen in 4 dimensions, and that's very interesting. Why? Because let's not forget that 4 dimensions is also the time dimension, time and space. So there's a temporal dimension. An easing model in dimension 4 would be linked to a physical object, the quantic field theory in 4 dimensions. So we have to be careful not to be bound by the physical dimensions, the a priori physical dimensions of the model, and not be afraid to go to a higher dimension, 4, 5, 6, 8, 24. Marina Vyazovska, for example, has had results for sphere stacking in dimensions 8 and 24. That's what got her the fields model. In 8 and 24, you really get what can best be described as miracles. It's beautiful mathematics. And let's move up a floor to the balcony. If there are any more questions. Oh, there are people up there, I see. Thank you very much. Congratulations, Hugo. We're so proud to have you in the university. My friend Yves Flukiger is right to be proud of his university. He's been so dedicated to this work. We see you standing by a blackboard on one of the slides, and that, of course, reminds us of the great mathematicians of the past who discovered all sorts of things. Marina has done her work. Well, what she's working on has been going on for 400 years. Today, when you see a picture of a scientist, you see a bank of computers, usually. Do you feel more comfortable working? Well, you say that there are all sorts of ways of working on a blackboard, but or do you also work on electronic media? Do you have modeling systems that where you use computers to validate your results? To some extent, you came to Geneva thanks to Professor Smirnov. Just after you arrived in Geneva, he was awarded the Fields Medal. Does that mean that now that you've achieved this success, does that mean that we're going to have to build a mathematics building for the next one? Are you planning to prepare the follow-up? Are you hoping to prepare others who will achieve the same distinctions or even greater ones than those that have been bestowed on you? Well, part of my research, which I didn't describe here in the slides, there is a part, this more imaginative and creative part of my work, where we try and build motivation. That is something which you can do outside an office. You don't know when it's going to hit you. I mean, it's a bit of a caricature to say that it happens under the shower, but often when you're doing something completely different, I sometimes feel that I have to get into almost a hypnotic state, self-hypnosis, where the brain is not doing anything else, and that's when the best ideas hit you. I never had an idea sitting in front of a computer. I panic when I sit in front of a computer, and the computer panics too, by the way. It's pretty complicated. Then there's the next stage, where you have to transcribe into mathematical language any idea that might have come to you. And here I'm convinced there's nothing better than the blackboard and interaction with other people. Mathematics is a spoken language, not a written language. You absolutely need to interact with others and have a blackboard, which is an area for sharing. It's very important.
il y a cette dernière étape, si vous voulez,
Then there's the very last stage when it comes to converting these ideas which you have now put onto the blackboard to convert them into a mathematical article, which is what you saw on the last slide, a formula or an equation. That can be done by a computer, but that's not the creative part at all. So there's very, very little electronics. Some mathematicians do a lot of simulation. I don't. Very little simulation, partly because I'm not particularly fond of computers, and also because I don't find it very helpful. I personally don't find it very helpful. Some people do use computers a lot. So much to answer your first question. As usual, I don't think I really did answer your question, but never mind. As for the second one, my research hasn't really progressed much in the last few weeks, and that annoys me a little bit, but the Fields Medal doesn't change anything in my research process. I'm still as motivated as ever. I still need people to come and interact with me, first of all because I want to transmit to them what I know. That's what researchers should be doing, and also because we get a lot from our students. They give us a lot. So if the Fields Medal can attract a lot of new people, that's wonderful. And then I'll be able to continue to engage in the science that I like. Not, I think we need to say that Fields Medal winners are often considered. I mean, the Fields Medal doesn't change the very high standard of the Department of Mathematics in Geneva. It doesn't change it, so we don't have much trouble attracting people, even without a Fields Medal. We even almost have to keep people out. There tend to be more people who want to come and study at Geneva University because of the high standard of the mathematics department. So I don't think the Fields Medal will change that. What about the stereotypic mathematician? The stereotypical mathematician who's antisocial and has read everything at the age of 10. Do you think we need to break that stereotype in order to encourage young people to go in for mathematics, get rid of that old stereotype? Well, I certainly am not like the stereotypical mathematician. I discussed this with some of my colleagues who opened university-level mathematics books when they were 10. When I think what I used to do at the age of 10, well, I think there's hope. There's no such thing as people who are naturally disposed for mathematics. There's not a particular characteristic. Every one of my mathematical friends are different. Pure intelligence is not always the key. You have to be creative, have a sense of aesthetics. Some people are more pugnacious than others. There's so many factors that go into the equation for making a good mathematician. I don't think there is. I think everyone, men and women, have the weapons to do mathematics. There's no one who's born to it. For example, the PISA study says that the French are bad at mathematics. A 30-year-old mathematician has lived for 30 years and has 30 years of experience, and I think that's the same for all scientists. Young women and girls should certainly not feel intimidated. There's no reason why they shouldn't become great researchers in whatever discipline. So you think there's a lot, a lot is down to personality. Yes, there's so many important criteria, so many different criteria that combine to make a good researcher. It's not a calculator, a mechanical calculator. That's not what we are. We're not calculators. Everyone can be a scientist, a researcher, maybe not in all disciplines, maybe there's room for everyone. You mentioned self-hypnosis. Yes, the ability to self-hypnotize. You said that there was punchy music when you made your presentation at the Fields Medal Award. Is there anyone above the fog who wants to come in with a question? Thank you for your presentation. I wonder, you presented percolation and phase transition, the two concepts. Is there a link? Yes, let me come back to these slides. I promise that I didn't ask anyone to ask this question. It wasn't a plant. Let me just... So there is a link, a strong link between the two. That's why I mentioned these two concepts. But I think... I left out a joke. I had to leave out a joke. I'm sorry. I'll get there. The link between the two concepts. Patience is a virtue. Patience. Here we are. This is what I wanted to show you. Indeed, there is a link between magnetism and percolation and porosity. Now, showing these two things here, it's perhaps not all that clear, but when we look at the mathematical models, you'll see that there's a very strong link between the two. I can't describe it because the mathematics are too complicated, but mathematics establish a link between these two completely different phenomena. In terms of physics, we have two completely different phenomena, but if we move up to the mathematical caricature, you'll find there's a direct link between the two. It's a sort of bridge. And that's what mathematicians like to do, build bridges between different objects. If you want to that's what mathematicians like to do. They like building bridges between everything. That's what probabilists and algebraists love doing. The advantage of having this type of link is that it's a link, but it's a link that feeds into both sides. For example, if I know how to do something on the magnetic side, I can also explain what's going on the coffee side. The mathematical machine that I have developed will also allow me, when I learn something about on the coffee side, on percolation, it will allow me then to draw conclusions for the magnetism side. There is a link, and that's the essence of my work, is to explain the link between the two and to take advantage of it. I think it's a very good demonstration of having two separate physical phenomena at the level of physics, and if you go up to the mathematical caricature, then there is a link between the two. There's another question at the top. There's a lady there and a gentleman.
I hope it's okay if I ask in English. My French is not really excellent. So I was wondering, the work that finally brought you the Field Medal, like how much time did it take, the project or multiple projects? And you talked about this shower moments of ideas. Was it like an assembly of multiple moments, or is there like one or two moments where you really remember that you had an idea that was really one of the groundbreaking ones, let's say?
Oui, donc je vais reformuler. Oui, tout à fait.
Okay. Let me reformulate it. That's an excellent question. Broadly speaking, how much time to represent the work that took me to the Fields Medal, or the results that were recognized with the Fields Medal? Was there a eureka moment, or was it a build-up of many different eureka moments, a sort of build-up? It all depends on the mathematician. Some mathematicians have one great result, which is recognized for a Fields Medal, awarded a Fields Medal. The recipient, the mathematician, is recognized for one great result, whereas I have a tendency to spread out a little bit. I have a tendency to move forward step by step, stage by stage. I don't have the strength or the confidence to go straight to the top of the hill. So it's a build-up, it's an accumulation of several results. And if you look at all the results that were recognized, despite attempts by the jury to focus on the last few years, these are all results that have been achieved over the whole of my career. Well, it's say over 14 years, which is not impressive in Nobel Prize terms, but anyway, over 14 years. And de facto, it's made up of many moments where individual problems were resolved. It's not one particular one, but several problems solved. And the moments that I saw personally as a eureka moment in terms of my brain and emotions, where I really felt, wow, now I've really discovered something. Those, as a rule, are not the moments when you solve the greatest problems. There's such a difference between an outcome or a finding which is going to be very important for community and other results that, or other solutions that one personally feels very strongly about. There's one result for me, for example, that was a very strong eureka moment. Vincent Tassot and I had that. It was an alternative proof of something that was already known. We just found an alternative proof. We tried to teach it. It was very difficult. We had been taught the same thing ourselves. We hated this theorem. It was an absolute disaster. We hated it. And one day, over a cup of coffee, once again, over a cup of coffee, we were just sort of bouncing ideas back and forth. We weren't even trying to solve this particular problem. We exchanged our ideas, and Vincent was talking about something which had nothing to do with the problem as such, and suddenly, in 10 minutes, we found proof and evidence that fitted onto one page, whereas the proof that existed in the past and that we were taught covered about 50 pages. Now, other people had already seen the proof, but we were able to prove it by a simpler alternative mean. So it's not... You just mentioned different methods. Sometimes the Fields Medal rewards one great result, which was the case for Stanislas, your doctoral supervisor. Yes, his discovery was a great result that really stood out. Two major results, and that's what got him the medal. Now ask him how long it took him to come up with those results. I have an idea, but I'm not sure. Certainly in my case, it was not one eureka moment. It was an accumulation of knowledge and results and findings and solutions. While we were preparing this interview, you compared your work a little bit to what an ant does, building more and more results. And can that lead to a paradigm shift, this accumulation? How you have, especially when you think that, when you bear in mind that your doctoral supervisor worked in a completely different way to yours. How does that work? Well, we get along very, very well. The more different one is, the better one gets along in mathematics, because you supplement each other. Some people would say, why on earth does Hugo, why is he so interested in this particular problem? But he has a more direct approach, and I had to solve 4 minor problems before getting there, but I had the necessary knowledge to be able to say, well, I think that's the way it is, and by putting it all together, as I said, compensating, supplementing each other. And with my doctorate, we got along so well just because we are different. For your students, too, it's so important. Teaching is an important role for a researcher. The teaching element is crucial because we have to put ourselves into the mind of the student and adapt to the student's way of thinking. So de facto, one is going to have to approach what one is teaching from a different angle. And it's this, and this is something one would not have done on one's own. That's why the interaction with students is so important. Another question. So would you like to, do you have a question?
Et ensuite, on s'arrête.
And after that, we'll stop. Well, congratulations. I was a little frustrated at the beginning. We saw a film that was in English and subtitled in English, and I was wondering why. This seemed to me to be redundant, and then I thought about what you said a little later in terms of fair is a transition. You talked about linguistics. I traveled in my mind. And Edouard Glissant says it's an aphorism. The same as sterile and the diverse is fertile. Is there a mathematical illustration of this aphorism, philosophical aphorism, in your experience? And then maybe more of a mathematical question. Is there a relationship between the percolation theory and the chaos theory or the fractals theory? So two questions. Regards the first, to keep the linguistic analogy. So I said that you have magnetism on one side, the Isling model, and then percolation on the other side with the percolation model. And you can imagine that these are two languages, a little bit as though you had French and English. I think you prefer this side, I'm sure you do. But the fact that there is a dictionary, this bridges a dictionary between the two, it means that you can use one or the other language to express yourself. And that is what is interesting. It is the contribution of the two languages that gives you this additional fertility that enables you to solve the problems in each of the languages. And fertility, of course, comes from diversity, there is no doubt. And building bridges is to be able to give yourself the possibility to speak different languages to solve a problem. What was the second question? Fractals. Well, that's interesting. You have one there. This is a random fractal. If we were to draw the edges of these white objects, we could see that these are objects that have a fractal dimension that is neither 1 nor 2, nor 3, nor 4. You know the dimensions, 1, 2, 3, 4. A line is a unidimensional object. The plan has 2 dimensions, etc. What you might not know is that there are objects that have dimensions that are different. And this is what we call fractals. So they're fractions, they're not full numbers. They're random, but they have dimensions that we try to calculate. This is part and parcel of the continuous phase transition that I was talking about a little earlier. It's a starting point of something. It's as of then that you can start looking at these objects in a different manner. We're going to try and understand the fractal dimensions, random fractals that are obtained from the Isling model. Well, thank you, Hugo. Thank you for your attention. Thank you to the rector. Thank you to Aurélie for this invitation. For those interested, and there are many of you, there is an autographed photo session by Johnny Depp. No, by Hugo Duminil-Copin, of course. And have a great summer, and above all, keep the fire burning. Thank you.